topic. Stereochemical non-equivalence. That means basically if they are on the same carbon, okay, but they're not equivalent. If they're equivalent, they don't split each other like the methylenes that we've been normally seeing. If you see a methylene and you put in an imaginary Z and you see that the protons are non-equivalent, they'll split each other. Okay, so they're like prochiral hydrogens. Okay, so for instance, if you look at this hydrogen and these two hydrogens, okay, if I had Z here, this hydrogen would be different than that hydrogen. These are prochiral hydrogens. And so what happens is these will split this hydrogen differently. Okay, so let's take a look. This methyl group is going to be a doublet because I have a carbon with a hydrogen on it, right? Doublet. That's my methyl. All right. Now what we find is that I have chemical shifts that are different for these three hydrogens, even though two of them are on the same carbon right here. So this one is right here. So let's take a look. This is split by that one, doublet. Split by that one, doublet. So I'm going to have a doublet of doublets. This one gives me a doublet of doublets here and here. This one, basically, you can see how it's not as pretty. Okay, so it looks like a 1, 2, 3, 4, 5, 6. So it looks like you should have 5, all right, hydrogens. 1, 2, 3, 4, 5. Now the reason it's not as pretty as these guys are is look at the tops. Okay, so what's happening is this. These two are splitting it slightly differently, but the coupling constant is so small you can't really distinguish it. So when you look at it, you say, oh, listen, I have a sextet. That means I have 5 hydrogens as neighbors. I then look at these guys and say, oh, they're 1 hydrogen each. It's a doublet of doublets. That means I see a hydrogen and a hydrogen. And if you look at your coupling constants, you can determine then what they are. Okay, so non-equivalent protons. So we see non-equivalent protons when we're looking at an alkene. We see non-equivalent protons when we're looking at something that's achiral. These guys are non-equivalent protons because this is prochiral. Time dependence. So basically there's tumbling occurring. So it's not like a solid state NMR. Because you see tumbling, things will average out. And that works to our benefit. But the other thing, though, is that we're not going to see splitting if there's transfer of protons. So when we say there's hydrogen bonding, there's transfer of the proton from here to solvent and back again. That happens so fast, it actually turns out you're going to start seeing it broadening out. Okay? And like with your cyclohexane. On the NMR time scale, we were talking about that earlier, and I still need to find papers for that. That is on the time scale for cyclohexane going from one chair to the other chair. It's so fast that for NMR, you can't tell the difference. They give a single signal. So to determine chair 1, chair 2 for cyclohexane, what we need to do is to find a different technique. Okay, so what happens? Ultra pure samples of ethanol. When I see it splitting, here's ethanol. So this hydrogen here, I have a CH3 next to it, so it should give me a quartet. But then I have a hydrogen here. So it's a quartet that's split here and here. Okay, so that's the quartet. It's split. Here, with the impurity, I don't see any splitting because this hydrogen has basically been exchanging with my acidic or basic impurities. Okay, so if you compare this quartet So basically, this one, you can see that it's not a quartet. You can see it's a pentuplet because I have 1, 2, 3, 4 hydrogens as neighbors. Here, because of the hydroxyl, the hydrogen here is exchanged out. It only sees the 3 neighbors here. Okay? So that's all we're saying is for those exchangeable protons. This one, here's my NH. Okay? Is broadened out. Usually amides are in this region. This is alkenes and this is amides. But look, it's broadened out and it's exchanged with solvent, so you can barely see it. This is a classic CH3 group, CH2, ethyl group. Because it's at 4, you know this is going to be next to an oxygen. So that's just classic. Okay? Solvent dependence, if we want to know if it's a hydroxyl group or an NH group, you actually dissolve your solute in some D2O, and the hydrogen exchanges with the deuterium so that when you rerun your NMR, you won't see the peak or it's much less intense. And we usually do this a lot when you're working with large proteins because basically you run it in your water, but you also run it with D2O so you can see which ones are exchanging out, and it cleans up your amide area and hydroxyl group area significantly so you can make sure that you don't get misassignments. Okay, so assigning the NMR and determining chemical structure. Okay. Let's look at chemical shift first. This is around 2.4. Singlet, 3 hydrogens. Okay. Must be, all right. So this is this group. If it's a CH3, it's going to be next to an electron withdrawing group, like a carbonyl, because this is a classic range for a carbonyl. This is between 7 and 8, doublet and a doublet. This is my aromatic region. The only way we get a doublet and doublet is if it's para-substituted. The reason is we have 2 different types of protons on a para-substituted aromatic. They'll split each other, so that's why you get the doublet, but we only have 2 different types, and that's why you get this beautiful splitting pattern. Broad singlet, almost at 13, that's got to be a carboxylic acid. So it looks like I have a paramethyl benzoic acid. Okay, this one. CH3, all right, broad singlet here. So this may be more of an amide, okay, because we know it's got to be an NH or an OH. This is 2 downfield being OH, more likely an NH, okay. NH2, like amines, would be more in this region here. Hydroxyl here, around 3.5 to 4.5. So amides run between 6 and 7. That's most likely an amide. Between 7 and 8, we see here 1, 2, 3, 4, 5. So we're going to say this is in my aromatic. I have an amide, 1 proton. So, and a methyl. So this is going to be an N-methyl benzamide. Your job for this lab assignment is to assign your chemical shifts, use your splitting, and use your integration to tell me what you think this has, what the structure is. Okay? So you have problems 1, problem 2, okay? And then let's talk about carbon 13 so we can do the bigger problem set. Carbon 13, carbon 12, even number, so it has no magnetic spin. Carbon 13 has an odd mass number, so it definitely has a magnetic spin. But remember, carbon 13 is only about 1 to 1.1% of the carbon sample. That's its natural isotopic abundance. Okay, the gyromagnetic ratio, so its effect is only 1/4 that of proton. So the signals are very weak, and they can get lost in noise. So either we have to enhance our samples by putting in physically carbon-13. We do that with proteins by growing our bacteria, our E. coli, in carbon-13 with carbon-13 glucose. But in this case, if we're just doing natural abundance, we have to take a large number of scans so we can average it and be able to distinguish the signals from the noise. Okay, there are a number of techniques. Okay, now one thing you have to be aware is that the peaks are not proportional to the number of carbons. What you'll find is that carbons that have a lot more protons attached to them will have the more intense peak. Okay, and the range runs from 0 to 230 ppm versus 0 to 14. Do we see splitting? Yes, you can see splitting on a carbon, but the splitting is not due to neighbors. The splitting on the carbon is actually due to the number of protons attached to the carbon atom. So it can make your carbon-13 spectra very complicated, messy. So we have different techniques. We have this thing called a proton decoupling technique. And what happens is that we scramble the proton signals, so all we see are the carbon signals and they don't get split. So then you can determine the number of unique type of carbon atoms in your molecule. If you don't decouple it and you see the splitting, again, it's an n+1, but it's not an n+1 for the neighbors. It's for how many hydrogens are attached to that carbon. So a CH2 peak will give you a triplet. Okay? Now, there's another experiment called the DEPT experiment, distortionless enhancement by polarization transfer. It's a big mouthful. And the pulses, so what happens is you do your pulse to get your signal, and then you pulse it again, depending on the angle of the second pulse to get the polarization transfer. You can either observe your CH only. So if you have any CH2 groups or CH3 groups, you won't see them. You can look and it'll tell you your primary, secondary, and tertiary carbons, but if you have carbons that don't have any hydrogens attached to the quaternary carbon, you don't observe those. So of the unique carbons that you see, you can say, okay, these are going to have hydrogens on it. Of those that have hydrogens on it, I know which ones are CHs only. And you can also do it so that your CHs and your methyl groups will be positive peaks for your carbon, and the methylene are going to, not methylene, but the methylene groups will be negative peaks. So in your carbon spectrum, you can say, I know which ones, are CH2 groups, CH groups, CH3 groups. I know which ones are CH, so I can distinguish between CH and CH3. And I know which carbons don't have any hydrogens on it. And that's all by DEPT experiment. If we look at your carbon spectrum, that's from 0 to basically 220, 230 ppm, 0 to basically, we look over here to 14 ppm. The trends are still, this is deshielded and that's shielded. So your alkanes will run around here. You start deshielding it. You just have larger jumps. Okay, so aromatics, the hydrogens are between 7 and 8. For the carbons, the aromatics and alkenes, aromatics tend to run around here, 120, 130, alkenes, 130, 140. So they're going to overlap in this range. In around 200, 210, 220, you're definitely going to see your carbonyl. Those are very unique. Okay, so knowing the trend of what happens with your functional groups as you go downfield is very important for both hydrogen and carbon. Okay, so let's take a look at this one. This is proton decoupled. This one is with the splitting. So you can see here at the 140, that one has no protons attached to it. This one, this is the decoupled. This one has a CH attached to it. That's why it's a doublet. Okay, your solvent is around 77. Okay, here, this went from a singlet to a doublet, so we know that has a CH group to it. This one I have 2 carbons. This looks like doublet, doublet, so it looks like I have 2 CHs, another CH. But see how messy this looks? It's starting to get difficult to try to determine how many hydrogens are on each of these carbons. Okay, so this part we'd probably need to do the DEPT. This one, you can see it's alkyl group. Remember, look at the chemical shifts around 10. CH3, because I have a quartet here. Okay, so this is just comparing. You can see how messy this is. So we need to do more different types of NMR experiments to actually get the total structure. But you can compare. You can say, I know this is a methyl group. These are more on the alkyl side. Okay, but over here, these carbons are going to be like an alkene type carbon, alcohol type carbon. Okay, so alkene, this one has this carbon is unique, has no hydrogens to it. This alkene has just a single hydrogen here. Okay, the hydroxyl carbon, remember, we said is more around in this region. So this one has a CH, most likely it's going to be right here. So alkene carbon, this one, that one, hydroxyl, and then here I have a CH3, but I don't know whether it's this one or these guys. Okay, so you can see 2 carbons that are very similar with CHs, but these are going to be hard to distinguish. It's these 3 that you can assign just from knowing your structure. Okay, let's take a look at this one. When you combine it, okay, so it's like being able to have multiple eyes. So now we're going to be using all of our senses. Okay, so see how high it is in aldehyde carbon, 180. This is going to be, I have a carbon double bonded to an oxygen. Very distinct. Does that make sense? Well, yeah, because look at between 9 and 10. Crystal clear. Aldehyde proton. If we know this is 1, that looks like it's 1, 1, 1. Okay? So I have 1, 2, 3, 4 hydrogens. I have 1, 2, 3, 4 carbons. Okay? So one of them's taken up in the aldehyde. So what about these guys? Well, this is the aromatic region, okay? And we're looking at aromatic, what is this guy? Okay, so I have hydrogen, 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 all right? 1, 2, 3, 1, 2, 3. This hydrogen's probably close to here. Now, my question for you, let's see if I do this, it's a plus, let me see, that's a minus. This one is most likely that one, okay? And these guys will be this one and that one, because if I have a minus sign there, so minus sign is going to make it upfield. Okay, so these 2 would be this carbon, or this hydrogen, then that hydrogen. What about this one? Remember we were talking about these guys can exchange. You may not be able to see him, and in this case, we don't. Okay? So, we don't see this NH. We see 1, 2, 3, 1, 2, 3, 4. All the ones attached to the carbon. 1, 2, 3. Okay, so aldehyde carbon. This is going to be in your aromatic ring. 1, 2, 3. Okay, so far so good. Let's see, we already saw this guy. All right, interpreting. So the number of signals tell you the different types of carbons. The location will tell you the environment. And the splitting will tell you how many hydrogens are on that carbon. All right, so here is 2-butanone. Again, see this for carbon? This is decoupled. This is basically your regular carbon. Single, so no hydrogen attached. Look at that. That's so nice. That's a 210. Just beautiful. Carbonyl. That's the first thing you think. Okay, I know one carbon belongs to the carbonyl. have 1, 2, 3 other types of carbons. 1, 2, 3 other types of carbons. Now, this one being at about, this is 10, about 8 ppm, we know it's got to be just like a regular alkyl group. And we know it's a CH3. It's got to be this one. It's not next to any electronegative group. Okay? Look at this. This is going to be less intense. Why is that? Fewer hydrogens? Maybe not, but it's less intense. Let's see. 1, 2, 3, 4. So this one has 3 hydrogens on it. Okay? So 3 hydrogens, another methyl group, but look at it. It's further downfield. It's that methyl group. This one, even further downfield, has 2 hydrogens as this one. So from something as clean as this, we can assign all the protons, or not all the protons, all of my carbons by inspection. What happens if it gets a little bit less clean? So you need all of your senses to determine what you have. So let's do an example using, we learned mass spec, IR, proton NMR, and carbon-13 NMR. Here's my mass spec. Now let me get my little whiteboard here. So my molecular ion, we can see 125, 130, 131, 132. This is the M+1, okay, and M+2. You can see the dramatic drop. So we know we have no isotopes, no bromine, no chlorine, no sulfur, because if I did, this would be higher. Okay, no iodine, I don't have large gaps. All right, so we already know this looks like primarily carbon, hydrogen. It's, let's see, 126, 7. Okay, 127. Wait, 130. What's there? 130, 132. 132. So it's not an odd number. So no nitrogen. So we're thinking carbon, hydrogen, oxygen. Okay. Now I lose at 131. You lost a hydrogen. So now we're thinking, oh, well, if I had an alcohol, it's unlikely I would have seen my M+. So chances are I have an aldehyde because I'm forming a stable acylium ion. The other thing is M+ is large. It's a fairly large molecule. I should see a large one. Okay, so now we're thinking, do I have a ring or something like that that helps to stabilize my molecular ion? Okay, so I'm thinking maybe an aldehyde because I lost a hydrogen. Okay, so this is going to be M+ minus an H. Now I have an arrow pointed to this guy, 103, right? So what's the difference between 132 and 103? That's going to be 29. So 29 is COH or C2H5. Well, if I suspect an aldehyde, then a COH might be good. So the 103 here might be whatever my molecule is where I cleaved off my aldehyde group. Okay. Well, what else do I have? I have, oh my goodness, I put an arrow at 77. So at 77, we know that's going to be a C6H5 fragment. So I know I have an aromatic ring. I also know that I have an aldehyde group. Okay, so 77 plus 29, that's 6, is that right? That's 77, okay. C6H5, 132, right? So 6, 106. So the only thing I can account for right now from our assignments, okay, is basically, that's going to be 26 atomic mass units for it. Okay, so that's the only thing that I'm not sure where it goes. That could be an oxygen. Okay, and then a carbon. That's 28. Nope, can't be that. It can be 2 carbons, 2 hydrogens. Okay, so we can have 2 carbons. So we can have a double bond, right? 2 carbons, 2 hydrogens. So 26, say, somewhere along the lines, I might be looking for C2H2. All right, so we're looking for an alkene. Right, so this is what this tells you. I didn't form 91, the tropylium ion, so I know I don't have a CH2 right off of my benzene ring, but whatever I cleaved right off my benzene ring, that means I have the C6H5. All right, so let's stop there. All right, 132, molecular ion. 131, I lost a proton. Most likely it's going to be an aldehyde. Makes sense because 103 is minus 29, which means COH. 77 tells me I have an aromatic ring, just the C6H5. Okay, let's take a look at assigning my IR. This peak is above 3,000. Oh, good. Means I have carbon-carbon double bond CH kind of stretches. sp2CH stretch. Then I have things below. All right. Maybe, let's see. I'm not sure that really is below. I don't know if I have anything below. Or if I have, it's very, very few. So let's just say, right now I know for certain I have sp2 carbon-hydrogen stretches. But see these guys? Remember we were talking about those vampire teeth? Isn't that an aldehyde, carbon-hydrogen, symmetric and asymmetric stretch? Oh, talk about a beaut. So I know this helps me to confirm my aldehyde CH stretches. I know I have sp2 carbon-hydrogen stretches. Look at that. 1680. This is a beautiful carbonyl stretch. So this plus that tells me, oh, aldehyde, spot on. Now, why is it at 1680 and not at 1710 or 1720? Maybe it's conjugated. Okay, so we have a conjugated aldehyde system. So it's got that aldehyde needs to be conjugated next to either my phenyl group or double bond, triple bond. But does it make sense? Internal triple bond? Maybe, because you couldn't see it, because it's internal. All right? But then that wouldn't make sense, because I had an internal triple bond, I'd be missing 24, not 26. So, more likely, double bond. Carbonyl, conjugated. Carbon-carbon double bond, stretch, okay. Aromatic ring, that's a nice confirmation. Now look at this. This also is pretty for an aromatic ring. 700, 750, most likely monosubstituted. Beautiful. So we have a monosubstituted aromatic ring that has a group that's conjugated with an aldehyde. Look at this. Okay, nothing below 5. Everything's up here. No alkyl groups? Great. We were wondering about that with the IR. Now we know. Aromatic, 7 to 8, 6 to 7, alkene, 9 to 10, aldehyde. Okay, so 5 hydrogens, so it's a monosubstituted benzene ring. So I have C6H5. What is on that carbon? Well, I have to have something on that carbon that's got carbon with a double bond. So I suspect I have benzene ring, carbon double bonded to a carbon, single bond, and then my aldehyde. Hydrogen, what's that? Also, this hydrogen is next to this one, which gets split. These are very large coupling constants, look at that. So we're thinking more likely this is going to be a trans than a cis. Okay? Now if you look at this, look how pretty that is. This one is going to be trans to that one. And this one is splitting that one. Okay? So, let's take a look at our carbon. I have 1, 2, 3, 4, 5, 6, 7 carbons. Okay, so this one for my aldehyde carbon. Then I have one here. That's going to be one of my, this looks like alkene, and I have basically my aromatic and alkene. So this is probably my alkene, alkene, aromatic, aromatic. 1, 2, 3, 4, 5, 6, 7. And gives me a total of 7. Okay, let's look in more detail about that example for structure determination using mass spec, IR, and proton and carbon NMR. So let me just draw out what we're talking about. This is my molecular radical cation. And what happens here is that that's at 132. Now I lose a proton to get 131. How is that possible? So one possibility then is this. If I have, this is my radical cation, and this electron goes with my hydrogen. So what I form, I'm going to redraw this for you in just a moment, is my cation here, and my hydrogen is a radical. But this doesn't actually appear at 90 degrees. What it is that I form an acylium ion, because now this is in resonance. Okay, so from the mass spec, there's an indication here that we may have an aldehyde group. And what we're going to do is we're going to look at the IR to confirm this. Okay, so what's the next peak? The next peak is at 103. Okay, so 132 minus 103 means I lost a fragment of mass 29. So how is this possible? Well, this 29 could be C2H5, okay, or it could be CHO. Well, that would be consistent here. So, if I have an aldehyde on my molecule, I lose a hydrogen, I form an acylium ion. I break this off, and that becomes my radical. Then what I have is I have this is my 29, is my fragment. Okay? Okay, so you can see that? Alright, so now let's take a look at the next peak. The next peak is 77. Okay, so this most likely lost a radical. Okay, bear in mind CHO or C2H5. This one loses an H. Okay? Now what about 77? So if we take a look at 132 minus 77, but I'm not going to spend too much on that, because what do we know about 77? We were looking at aromatics. And what we know is that this is typically C6H5. Okay? So we're looking at 77 being C6H5. And typical for aromatics so also 51 is indicative of an aromatic. Let me just write it out of aromatic ring. Okay. Okay, so when this rearranges and it loses C2H4, H24, so C2H2. Okay, so we do see this peak, although we don't need to assign it. So what's going on here? So it looks like I have an aromatic ring. Now this is what I'm going to explain. So when I have my aromatic ring, if I had a CH2 here, an alkyl methylene, then I would form the tropylium ion. So we would see a mass charge ratio of 91, but I don't. Okay, that is not present. Therefore, whatever is attached here, okay, this is not an alkyl carbon. Okay, so now we're thinking maybe it's going to be a vinyl carbon or alkynyl carbon. Okay, because we don't form the tropylium ion. So from my mass spec assignments, what kind of information do we know? From mass spec, we know we have an aromatic, okay, we know we have an aldehyde, and we know that our, okay, we know that our molar mass is equal to 132. Excuse me. This is 29. This is 77, which means that the difference is 26. So we need something that adds up to 26. Well, carbon and oxygen are 28, so it can't be carbon and oxygen. But just think, a C2H2 fragment has a mass of 26. This means that I have something like this. That makes no sense because I have to attach an aldehyde to it. So the only possibility then is that I have in this molecule something like this. Do I know it's trans? No. I'm just drawing it that way just because. You could draw it cis. But we're looking at something like this. That would make sense because I would cleave here to get 77. I couldn't cleave here and get the 91. I would lose my hydrogen. I'd form my psyllium ion. So let's keep in mind what we're thinking about for this. Now, let's take a look at the IR. The IR, okay, we have to assign a peak around 3050 wave numbers. Well, that's an sp2 carbon-hydrogen stretch. Then we have, oh my goodness, this is gorgeous. Can't tell you how beautiful it is. 2700, 2800 wave numbers. This is definitely my aldehyde CH stretch. Just perfect. Nice vampire teeth. Okay, then I have something at 1680. It's very strong. This is a classic carbonyl stretch. Okay, but before we move to the next peak, let me ask you this. Why is it 1680 and not 1710 or 1720, which is more typical? Okay, why? The reason it's not 1710 or 1720, which is more typical, because this must be conjugated. And so my wave numbers go down. Okay, may lower. Okay, so there's some consistency here. Okay, then we look and we have a 1600 wave numbers. That's my carbon, double bonded carbon stretch. Okay, and then I see a peak at about 1485. I'm not asking you to sign that one. That's my typical scissoring, right? Well, is it really scissoring? I'm not sure. Okay, so let's hold off on that one. Okay, we see other ones that you're not supposed to assign just because we're getting to the fingerprint region. Talk about the fingerprint region. I have an arrow indicating around 700 and 750 wave numbers. Okay, and if you go back to the aromatics, this is an aromatic out of plane. Okay, bending, wagging. Okay, so two things about this one. It confirms your aromatic, but by itself it's not going to tell you absolutely and definitively you have an aromatic. What you're doing is you're accumulating all sorts of circumstantial evidence to show what you have. So that's one of it. Okay, the other thing is with this pattern, you're going to look at your slides and you say, oh, wait a second. This may be monosubstituted. Okay, so again, this confirms what we're suggesting from our mass spec fragmentation patterns, and we also think there's a monosubstitution. Let's take a look at our proton NMR. There's nothing upfield of 5, but what we do see is we see at about 6.6 ppm, we see a doublet, and it's 1 hydrogen. Now we see about 6.8, let's say, ppm. We see another doublet. Okay, and around 7.5 ppm. It's a multiplet, it's pretty messy. It's 5 hydrogens. Okay, and then around 9.6 ppm. You see a doublet. Okay, so that's 1 hydrogen. Okay, so what do we see here? Let's talk about my chemical shifts. This range between 6 and 7. This is typical for alkene CHs. Okay, between 7 and 8, it's typical for aromatic H's. Okay, and at 9.6, between 9 and 10, this is typical for an aldehyde H. Okay, so we have an aromatic. I have 5 hydrogens on my aromatic. These are my 7.5 ppm. It's a multiplet. These are different than these protons, which are different from that. So these guys get a doublet. This one gets a doublet, and a doublet, and okay. Of doublets, this one gets a triplet. So that's why it's so messy. Okay, because they're slightly different, and they're all on top of each other. So it's really going to be hard to separate those out. But that's in the range, and they're very close together. Now, I have an aldehyde right here. That's basically truncating my molecule, because I can only, if I put it here, where am I going to put the rest of my alkene? So it's got to be at the end. So I have an alkene here. I have one hydrogen and one hydrogen. And I can write CH. That would explain the difference. This one is deshielded by my carbonyl. This one's deshielded by my aromatic. So they're not identical. They're separate. Okay. This one is only split by this one. So I get a clean doublet. This one is split by this one. And also 1, 2, 3. It's a J3 coupling. So this is split and this is split. Okay? So if you look, the one at 6.6 ppm looks like it has a little bit more peaks to it than this one, the one at 6.8. So my suspicion is this is my 6.8, this is my 6.6. But right now, the NMR isn't clean enough to be able to look at the coupling constants to tell you exactly which one is which. It does look like there are large coupling constants, and as we saw with styrene, if it's very large, it could be, they're not, you know it's not going to be geminal. So about 15 hertz for trans, about 10 hertz for cis. Okay? So that's our proton NMR. Let's take a look at our carbon-13 NMR. So now we have a really good idea of our molecule. We knew from mass spec what some of the fragments are and the differences in mass, so we can figure that part out. Then from IR, we saw we had the alkene stretch, we had the aldehyde stretch. Those are all beautiful. What was nice is if you know your fingerprint region, then you can probably take a look at that pattern to see if it's monosubstituted. NMR nails it. Let's take a look at my carbon-13, and I'm going to leave the structure up. Okay. So for the carbon-13, I have 1, 2, 3, 4, 5, 6, 7 unique carbons. 1, 2, 3, 4. These are the same. 5, 6, 7. Okay, so that's great. Now we see something at about 195 or so. 170, yep, about 195 ppm. Oh, that's got to be my aldehyde carbon. No doubt about it, right? There's one that's about 152 ppm. Okay, and then you have a whole bunch. You have 1, 2, 3, 4, 5 between 128 to 135 ppm. Okay, so in that range we have 5 of them, 5 carbons. We have 1 carbon here. So alkene carbons tend to be slightly more downfield than the aromatic carbons. This is most likely my alkene carbon. Okay, so you would probably have to just determine which is more electron withdrawing. And so basically we were saying which one, it was hard to distinguish between this hydrogen and that hydrogen. So you would pick one of those for the 152. My guess is probably that one. And then for the range closer to the aromatic, these 5 carbons, 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5. That would be in this range. And you would just block those off. And that's how you would assign your spectra, and that's how you would determine your structure. Okay, so good luck on your dry lab assignments for structure determination. It's just doing a jigsaw puzzle, and actually you'll find it's a lot of fun. So let's go through. When you're done with this, what it looks like then is this. Let me just go to the end and show you what I think it's going to be.